Lesson 29, demo. Today we will continue to work on related rates problems last seen 2 classes ago. Ship A is sailing north and ship B is sailing east. Let's take our quick look at this picture here. So ship A is the one going north. I'll put the A over here going this way, and then B is going east that way. Using an XY plane, radar records the coordinates at each ship. Approximate the rate at which the distance between the ships is changing at t equals 5. First, let's see if we can understand the relationship between the picture and these two tables. So you can see that the times start at 1.25 and go up by 1.25 until we get to 5. Same times over here. And so at 1.25 minutes into this experiment, this particular ship, ship A, was located at an X of 1.77 and a Y of 2.64. That's this point right here. And then at 2.5 minutes, the ship was at the same X is 1.77, but now the Y is 2.97 right over here. The other 2 points are plotted. And then the same deal over here, you can see that in this case, the Y's are always 1.24, which is why this ship is moving on the same horizontal line. And so we're interested in the rate at which the distance between the ships is changing at t equals 5, which is that last point that's drawn there. And so you can see, I'm going to erase these in a second. Well, actually make them disappear. So the two ships are a certain distance apart there, and then 2.5 minutes in, that's the distance between them, and then 3.75 minutes in, it's that distance, and then 5 minutes in, it's that distance, and you can see that the lengths of those blue lines are changing, but probably not at a constant rate. So clearly we are interested in the rate at which the distance between these two is changing. I've connected the last two, but really you could connect any two, just pick two corresponding points. And so because we're interested in that rate, it sure feels like we should give a label to that thing right there. So how about we call that one C? And when it says the rate at which the distance is changing, it is asking for dc dt. So we've symbolized what we are after. And I sure feel like there's a triangle here waiting to be drawn. So I'm going to draw in this triangle. I'm going to draw vertical, not all the way to the x-axis, but just down far enough so that it's going to be on the same horizontal as the B ship is. And now we will draw the rest of the line for B here. We've got this beautiful right triangle. And because we're given up here, you know, like distances with X's and Y's in them, it sure feels like labeling these sides as maybe A here and B down here is a good idea. And now the equation that we're going to come up with is, of course, the Pythagorean theorem. A squared plus B squared equals C squared. Now this one, like I don't have anything else written down. I don't know what to do with any of the numbers in the table. Like typically you'd have, you know, like maybe dA dt equals something and maybe B equals something. We don't have any of that. Frankly, I don't know what I need just yet. So I'm ready to hold off on like writing down the givens of the problem and just take a derivative of this A squared plus B squared equals C squared. So let's go ahead and do that. Remember, A, B, and C are all variables, with time being the independent variable lying underneath all of them. So the derivative of A squared is 2A times dA dt plus derivative of B squared, 2B dB dt equals derivative of C squared, 2C dC dt. Okay, so I'm going to go ahead and divide everything by 2, which is going to get rid of all of these 2's. It's not necessary to do that, but just makes it a slightly easier calculation for us. Okay, so I'm going to circle the thing that I'm looking for. Remember, dc dt was the question mark. So this is the thing that I want. And that means that every other quantity in this equation needs to get substituted by a number, right? Everything else has to become numbers so that we can just solve for dc dt. Okay, so I think some of these numbers are actually pretty easy. So for example, remember it said that we're focusing our attention on the moment when time is 5, which is actually the moment that this particular triangle here captures. So instead of treating it like the dynamic changeable triangle that we were, let's fix it in this one frozen state right here. And can we calculate the actual length of that orange segment, which is A? I think we can. So at the top here, we've got whatever the y coordinate is of that last point, and at the bottom here, we've got the y coordinate of all of the B points, which are all the same. So I'm going to highlight the two numbers we're focused on here. So the y coordinate of the top point for A It's 3.67. And the y-coordinate for every point for B, I'll just highlight it here, 1.24. And we just have to subtract those. And so then we can write down here that the value of A at this fixed moment in time is simply 3.67 minus 1.24. So 2.43. Okay, and then the same deal for B. Maybe pause the video here if you haven't had a chance to do this calculation yet. See if you can figure out how to calculate the value of B at this fixed moment in time. Okay, so if you're back, then I think the way that we're going to calculate B is to look at how much the X value is at this last point, and then how much the X value is for any of these points. They're all the same. So we'll highlight here the X value for the last point for B, and then the X value for any point for A. So we subtract those numbers. So B is equal to 6.08 minus 1.77. I get 431. Okay, and then how are we going to calculate the value of C at this fixed moment in time? Well, this one I can't just do a simple subtraction like I was doing up here, but I do know the particular value of A at that moment is 2.43, and I know the value of B, and I do have my Pythagorean equation. So that's what we're going to do. So 2.43 squared plus 4.31 squared equals C squared. And let's go ahead and use that to find the value of C. Okay, so that's C squared. We're doing the square root of that thing, so a little less than 5. Let's call it 4.95. I'm going to store this as C just in case we need it for a future calculation here. But we'll call it 4.95 when we write it down. Okay, so I think we've gone as far as we can in terms of finding A, B, and C. Those ones are good. And so remember, the goal was to fill in every single one of these expressions except for the circled one here. We got to get numbers for all of them. So we just found numbers for A, B, and C. So the only things missing are numbers for the rates of change, dA dt and dB dt. Okay, let's take a look. Well, how fast is this line segment's length changing? That's what dA dt represents, and you can see it moves, it's the same time intervals here, so it doesn't move that much in this first time interval, then it takes a bigger jump in this next time interval, and then a smaller one here. So how are we supposed to approximate the ADT given the limited value, the limited information we have in the table? So all we're going to do, we're looking for the rate at which these numbers here are changing as time passes. So all we're going to do is focus on the times that we have that are as close as possible to t equals 5. And so I've got the information at t equals 5. Clearly we want to use that. And then the nearest available time to that t equals 5 is t equals 3.75. So all we're going to do is calculate the rate at which the this y coordinate is changing as time passes. We can ignore the 1.77s. They're not changing. And we're just going to assume that whatever speed the boat is moving in this little 1.25 minutes, it's just going to continue to move at that speed, or at least at this one moment in time, t equals 5, its speed probably isn't all that different from the average speed in between these last 2 points. So we are approximating now dA dt is roughly equal to, so we're looking for, it's just a change in y over a change in time. I'll write it this way, change in y over change in time. And so the change in y is the 3.67 minus the 3.42. And the change in time is just 1.25 minutes, but I'll just put the actual numbers here so we can see the similarities between top and bottom of our fraction. So 5 minus 3.75. Okay, so I'll type that in the calculator in just a moment. But while we're here, let's go ahead and do the same kind of calculation for dB dt. So B is changing, the length of this line segment here is changing because the x coordinates are changing. And so I feel pretty good saying that what we're going to do is do a change in x over a change in time here. So again, focusing our attention on t equals 5 for the second table now. Clearly, we're going to use this information when t is 5, and the nearest point that we have is the same 3.75. Again, we can ignore the 1.24s. They aren't changing. So we're just going to do change in x over change in time. So 6.08 over minus 5.78. Divided by the same 5 minus 3.75. Okay, so let's use our calculator to get some decimals here. So 3.67 minus 3.42. I'm not doing good things. 3.67 minus 3.42. And then we'll divide that by the 1.25. So I think that's just going to be a fifth, or 0.2. And then the other one, 6.08 minus 5.78. And then we divide that by, again, the 1.25. And we get 0.24. So 0.3 and 0.24. Okay, and now I think we have every single thing that we need for our equation. So I'm not gonna, well, yeah, I guess we've got just about everything on the screen now. So let's go from here. So we are using this big equation right here, and we are plugging in numbers for all of these things that are variable expressions. So here we go. I've crossed off the 2, so not reading that, but A, we calculated A already. That's 2.43 in orange, times the ADT, that is the 0.3, plus B, that's purple, 4.31, times dB dt, that's 0.24, equals C. C is roughly 4.95, and then dC dt is our unknown. And so that's the only one that doesn't change right now. And so I think we're good to go here. We're just doing the arithmetic on the left side and then dividing everything by 4.95. So this will be our final answer here. Okay, so we got all that, and we're going to divide it by, now 4.95 was an approximate value, but I think we actually stored this as C. So if I just say divide by alpha C right now, it'll give us the best answer it can. So we'll say about 0.356, 3564. And we'll get some units here. So it's C units over T units, miles per minute. So that means the ships, the distance between the ships is increasing at around 0.3564 miles per minute at that one time T equals 5. It would be interesting, since we've done a bunch of the calculations here, it wouldn't be too hard to answer the same question at T equals 1.25 or 2.5 or 3.75. Be interesting to see, are the distances changing at basically a constant rate, or are they changing slowly and then faster, 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 or fast in the beginning and then slow at the end? So you can play around with that later if you'd like. So the activity today is to continue working on that homework that we started the other day on the first related rates day. So go ahead and try to sit near people or work with people that are around the same place in that homework assignment as you are. And if you finish all of that homework already, there are 4 problems in the activities on the starting on the next page. And there will be a video posted of me solving those 4 problems, so you can check that out if you get stuck.